Okay.
Hello
Hello
everyone, good
everyone. Good
morning.
morning.
My
My
name
name
is
is
Wei
Wei
Kai
Kai,
and I'm
and
from the
I'm from the
Primary
Primary
University of
University of
London and
London and
supervised
supervised
by
study by
Short Fu, and
Shortcom and
this work
this
is
work is
collaborate
collaborate
also
also
with
with
the
the
Adobe Research and the Peking University. And
and
firstly, we would like to introduce these tasks. In this paper, we work on the task called video moment retrieval, also known as natural language video localization or video temporal grounding. It means to locate a temporal moment semantically in a long and trimmed video by predicting its start and end time in indices according to a natural language query sentences. Considering it requires not only deriving the semantic correspondence and alignment between video and text, but also recognizing the subtle visual similarities among different moments in the same unstructured videos of shared context. So this task has their unique challenges. Okay, and here is an example from the short dataset. For example, we have a video which length is around 20
around
seconds,
20
and
seconds.
here is
And
the
here is
raw
the raw
video
video
here.
here.
Yes, and we have one VMR model, and we have a query, and the text is person sits down on a chair, and we want the model to locate what the moment in the videos, and we want and the target output is temporary around 13 to 20 seconds, and here is the segment. Yes. Yes, that this is a sub video of the whole video, and that match the semantics that the query saying person sits down on a chair. So to achieve this target, it requires the VMR model to accurate comprehension of visual and textual modalities and their precise cross-modal alignment. And as the cross-modal alignment information is provided by the labeled dataset, then we look deep into the VMR dataset currently. And there are several challenges or difficulties when building a VMR dataset. Firstly, annotating a VMR video dataset is much harder than labeling images due to the time ambiguity. This is an intrinsic characteristic of the moment because the moment is transferred smoothly in the video between different frames. Secondly, labeling VMR dataset is label intensive and time consuming. As it is a video task, the annotator needs to go through the whole video, which is usually several minutes or even or even over an hour, and they will spend more time on one annotation than on image annotations. And there are several widely used VMR datasets, and we list them in the table. And we can see the number of videos is from 100 to 20,000, and the queries are tens of thousands, and from different domains such as homes, lab kitchens, and so other things. But all in all, the VMR dataset is relatively small, especially compared with image datasets such as the Cochrane or the ImageNet. So the cross-model information provided by the small VMR datasets has some dataset level statistic regularities due to the limited scale. The cross-model regularities include the moment annotation in existing benchmark datasets fall into several species times in both train and test splits. As is shown in the left figure, the moment starting and end points fall into several points and share similar regularities in both train and test set. That will give a model a shortcut to do the task from the regularity. And secondly, the video sentence pairs have strong correlations between the ground truth target moment location and the text query. as is shown in the right figure, the overall distribution of the start and end points in the short STs look like this. However, the moment related to the query open will usually fall at the beginning of the video, just like this. And the query includes the leave will usually fall at the end of the video. However, this is not always be true in real-world scenarios. We can have many shots in a long video, and the moment related to the open will not always at the whole video, maybe in the middle or the end or such other things. So, based on this, the temporal bias problem is that defined as the one VMR model tends to retrieve the corresponding moment based on some dataset statistical regularities instead of semantic video text alignment, and will perform full generalization ability against different distributions. This is also showing that the ID, the independent and identical distribution assumption is somewhat fragile to existing methods and does not always hold in more complex and real-world scenarios. Recent attempts on debiased BMR methods can be divided into two categories. One is to explicitly change the temporal distribution in one video sentence sample pair by directly clipping the video and then discarding some parts or recording the sequences of video segments on predetermined time points, just like this. This is the reorder. We will move the movement to at the end of the video, and then we discard some irrelevant parts to construct a new video to relatively change the movement distributions. However, to balance the impact of certain dataset-wise regularities, this approach arbitrarily destroys sample integrity. In this case, the long-term temporal semantic coherence between different segments in each video sample, which is meaningful and helpful for accurate moment localization, is destroyed. Because we reorder some parts temporarily or discard some parts, then we'll have some information loss. And the other category is to capture the impact of the temporal bias on model learning through self-evaluation and restrict the importance of some video query sample pairs in the training iterations. However, it overlooks some samples cross-model information during training. Even though the video text information in these samples is useful, but this method also not use them but overlook them. So this category will cause avoidable waste in the very limited and valuable small data sets. And all in all, both categories are incorporated when utilizing samples from the existing limited and valuable BMR datasets, whose labeling is extremely time-consuming and label-intensive. So in this work, our key ideas, instead of sacrificing samples integrity and cross-model information to transfer training set knowledge along a predetermined direction and balance such performance on certain target distributions, we present a testing the temporal feature perturbation and refinement model to augment each video query pair by temporal perturbation without certain directions. And our model encourages our method encourages the model to learn more generalizable cross-model match information to alleviate the temporal bias problem in current methods. In our cases, the target temporal distribution is agnostic. And here is the whole framework of our method. We first designed a frame-level temporal feature perturbation (FFP) to augment and diversify each video sample to a video representation space. And by perturbing the video feature on the temporal frame-wise feature distribution scope. In other words, the mean and variance along the temporal dimension. The new video feature representation sampled from the space diversified informative domains. In this case, the training and the test sets, and encouraging the model to learn more generalizable cross-model alignment knowledge. And furthermore, given the intrinsic ambiguity of movement boundaries, which we mentioned in the previous slides, there will be a plausible boundary shifts in perturbed video text pairs whose temporal distributions are diversified. We propose another model to augment the boundary temporal labels to a candidate endpoint sets by a proposal-based perturbed auxiliary branch. Given a perturbed video, we construct a query triplet to refine the boundaries and to get the model more precise semantic training. And the first part is a frame-level temporal feature perturbation. Given an untrained video and the natural language query, we got the video representation by a pre-trained CNN model and use the globe word embeddings as the word level query features. We first get the mean and variance of video representations along the temporal dimension. The feature statistics capture informative characteristics of a certain domain. In this work, we propose to create augment representation scope by perturb the temperature statistics. In other words, perturb the mean and variance. And we perturb like as this formula and follow a normal Gaussian distribution. And where the epsilon mu and epsilon are random sampled from a standard normal distribution and separately to produce the normalized magnitude of the perturbation. And the perturbation intensity is generated from the batch-wise. And the study and in the standard deviation between the batch-wise different features contain implicit semantic information, and the direction of large difference suggests the possibility of more meaningful semantic changes. So we'll collect the videos from a mini batch of B samples and calculate features statistics along the time dimension correspondingly, and concatment. And then the perturbation intensity calculated as the second formulas. Okay, and to maintain temporal static meaning and contextual coherence in the video frame sequence, beyond the perturbation intensity, the direction on the one video feature are presented to be consistent. And we perturb the VP by shifting the time-wise distribution on each frame consistently as in the third formula. And here we go through on the first part. And second part, because there is some plausible boundary shift in perturbed videos, we construct a triplet video inputs, including a positive query and two negatives. The first is negative non-matched query sampled from the mini batch, and that is not matched with the current video. And second is a null without query, so-called the video only. And we monitor the training by capturing any potential inclination of ignoring utilizing cross-model information and refine the final training loss. And the experiments are conducted on the Schwartz XT and ActiveNet captions, which are two widely used datasets in the VMR task. And there are two splits, which is so-called test OD, which relocated the testing splits, which ground truth moment distributions is different from the training. So it is an out of distribution test. And second, we also have an IID test. satisfies the independent identical distribution as the training splits. And the video and the text encoders and metrics are listed here. And we can, from the comparison with the sorters, we can see in all text OD splits, both thrust and activity nets, we can see we outperform almost all the sorters and our baseline method, which shows the TPR effectiveness to address the temporal bias and the generalizable performance when facing out-of-distribution test splits. And we also have some better results on the test ID splits, which shows our perturbation can augment the sample space and promote more precise and semantic cross-model matching and alignment. And also, there have some more ablation studies about the combination studies in our methods, and there are some triplet design and the perturbation design, and there is also a figure about the perturbation intensity. And here is a visualization of the of our method. The right figure, this figure shows the temporal distribution of undressed in thrust split, whose moments are usually located at the beginning. We can see the red is the heat map that we usually have the undress on the beginning in the training sets. However, the baseline method, the green line, the baseline method, the red line will follow the regularities to locate the undressed moments at the half part, the first half part of the videos. And our methods can effectively mitigate the reliance on the regularity and turn the model focus back to the semantic video test alignment. And this is one visualization from our methods. And due to the time limitation, and that's all my representations.
Thank you very much. We have time for perhaps one or two questions.
So, even when you show your perturbation and then you're using the gamma function,
yes,
it's not really a gamma function. It's just a Minkowski inequality, right?
In
the space.
Yes, exactly.
They called it a gamma, but it's not really a gamma, right?
This gamma is following previous formula. That is calculated as the let me see that they call it the standard deviations. This is not the gamma that you mentioned. And this we use the gamma function to represent the standard deviations. Yes.
In OP space.
Sorry?
In OP space.
Yes.
Does the method only applies to when you're looking for a single action from a single agent? I was thinking, what happens if you have competing actions in the same video? If you're looking for someone who is standing up.
Yeah, this
one is standing up, the other one is sitting down, etc., etc. It's slightly more complex. That's the question.
Yes, I agree. In current data sets, the one maybe relatively strong hypothesis that is the query-related movement is only one. But there are several other data sets that have some very similar movements that are related to one query, and we currently not work on that. Yes.
Many years ago, someone, I don't know if the story was true, but someone told me that in, let's say, the Discovery Channel, what they do is they have teams in Africa just filming anything they want. And it all goes via satellite to somewhere in the United States, where a producer would say, now let's do a series about I don't know, lions and how they compete against hyenas. And they would have terrible issues about finding the moments they might want in order to create a narrative for their story. I mean, have we made progress in that? Is this something you could eventually do?
I think, yeah, that was some of the companies like, it's like, I think not from broadcasters. Broadcasters the data probably not as widely accessible. BBC just released quite large multimodal data sets, but there are still a lot of limitations. We'll have a look at it, and it's not totally categorized, but they have very long. BBC released the data sets all the way back from 1924 up to date, but it's massive. So the actual work on it it's been very limited. What the companies have been doing, which are more closer to this, like Adobe and some other known companies, but I'm not allowed to mention names. It's searching for social media and also online interactive conversations. So they have rather than but there are similar type of problems.
Okay. Thank you very much.
Thank you.